In this video, we're going to talk about how to graph polynomial functions using things such as end behavior, multiplicity, and even finding the zeros. So let's begin by taking down some notes first. Let's begin our discussion with the graph of y equals positive x squared. So this is an even function with a degree of 2. Even functions are symmetrical about the y-axis. And so this is the shape of the y equals x squared graph. The end behavior towards the left is up, and the end behavior towards the right is up. Now there's other ways in which you can describe the end behavior of this graph. On the right side, as x approaches positive infinity, y approaches positive infinity. So here's how you can visualize it. As you move towards the right along the x-axis, as you go towards positive infinity, the values along the y-axis are increasing. You're going up towards positive infinity on the y-axis. Now the end behavior for this graph on the left, as x approaches negative infinity, y approaches positive infinity. As we go to the left, we can see the y values are increasing. So this is another way in which you can describe the end behavior of that graph. Now let's consider another example. In this case, it's going to be y equals negative x squared. Now this is also an even function, so we're going to have symmetry along the y-axis. But we have a negative sign. The leading coefficient is negative, so this is going to reflect over the x-axis. So the graph is going to look like this. As we can see, the end behavior on the left is down, and it's also down on the right. But we can express it this way, just like before. So on the left side, as x approaches positive infinity, that is, as we go towards the right, what happens to the y value? Well, we can see that the y value is decreasing. It's becoming more negative, so it's approaching negative infinity. So that's the end behavior. I put left. This should be on the right side because x is going towards positive infinity. So that's the end behavior towards the right side. Now towards the left side, that is when x goes to negative infinity. So we're going towards the left. Notice what's happening to the y values. They're also becoming more negative. So y is approaching negative infinity. So that's one way in which you could describe the end behavior of a particular graph. Now for the sake of practice, go ahead and describe the end behavior for these two graphs. Y equals positive x cubed and y equals negative x cubed. And I'll give you the shape of these graphs. So positive x cubed looks like this. It starts from the bottom, and then, let me draw this better. It curves towards 0. It's actually almost horizontal at the origin, and then it goes back up. So right here, you have like a horizontal tangent. Now for y equals negative x squared, it reflects about the origin. So it looks like that. And we still have that same horizontal tangent where it touches the x-axis. So go ahead and describe the left and the right end behavior for these two graphs. So let's start with the left side. As x approaches negative infinity, what happens to y? Well, as we go towards the left, we can see that the y values are becoming more negative. Y approaches negative infinity. Now for the right side, as x goes to positive infinity, y goes up. It goes towards positive infinity as well. So that's the end behavior for positive x cubed. Now let's do the same for negative x cubed. As x approaches negative infinity, what happens to y? As we go towards the left, the y values are increasing in the positive y direction. So it goes towards positive infinity. It's going up. And for the right end behavior, as x approaches positive infinity, as we move towards the right side, we can see that the curve is going down. So y approaches negative infinity. So now let's put everything together. Let's start with the even functions. So y equals positive x squared. What you need to know is that the end behavior is up, up. Now the same is true for y is equal to positive x to the fourth. This graph looks similar. The end behavior is up on the left and up on the right. So anytime you have a polynomial with an even degree and a positive leading coefficient, the end behavior will be up, up. Now, if we have negative x squared, that does not look like a 2. Let's do that again. The end behavior is going to be down on the left and down on the right. So I'm just going to use D to represent down. Now for y equals negative x to the fourth, the situation is similar. It's going to be down on the left and down on the right as well. So anytime you have an even exponent, it's either up, up or down, down. The difference is based on the sign of the leading coefficient. If it's negative, it's down, down. But if the leading coefficient is positive, it's going to be up, up. Now let's consider the examples where the exponent is odd. So going back to positive x cubed, the end behavior is down on the left, up on the right. Now this is similar to y is equal to positive x to the first power. But this is going to be a straight line. But the end behavior is still the same. It's down on the left, up on the right. So anytime the exponent is odd, the end behavior is going to alternate. It's going to be either down, up, or up, down. If the leading coefficient is positive, it's going to go from down to up. So it's going to be increasing. Now, if the leading coefficient is negative, we're going to get the reverse situation. So instead of going from down, up, it's now going to be up, and then it's going to go down. And the same is true for y equals negative x to the first power. It's a straight line, but it's going to go in this direction. It's initially up on the left, but it's going to be down on the right. So now let's summarize this in a table. You may want to write this down. So when the exponent or the overall degree of the polynomial function is even, and if the leading coefficient is positive, the end behavior will be up, up. If we have a degree that's even, but the leading coefficient is negative, then it's going to be down, down. That's the end behavior. Now, if we have an odd degree with a positive leading coefficient, it's going to be down at first, and then it's going to be up. If it's odd and negative, it's going to be up and then down. Now let's talk about the behavior of the graph near an x-intercept. I'm going to explain this more later in this video, but for now, you want to write this down. So let's say the multiplicity of a particular x-intercept or a particular 0 is 1. this is going to look like the graph y equals x to the first power. So at that 0, it's simply just going to cross the x-axis, basically in a straight line. Now the angle of the straight line can vary, so you don't have to be too specific about that. If the multiplicity is 2, it's going to look like the graph y equals x squared. It's not going to cross the x-axis, but it's going to touch or bounce on the x-axis, much in a similar way to the graph y equals x squared. If the multiplicity is 3 for a particular 0 or x-intercept, it's going to look similar to x cubed, but at that x-intercept. So if you think of the graph of x cubed, it looks something like this. So you're going to have that same shape here, but you're going to have the behavior at that 0 is going to be horizontal. So make sure you understand that if the multiplicity is 1, the behavior at the x-intercept is going to be like a straight line. It's going to cross the x-axis in a straight line. If the multiplicity is 2 at that x-intercept, it's not going to cross the x-axis, but it's going to bounce on, that point. And then if the multiplicity is 3, it's going to cross the x-axis, but not in a straight line, but rather with a horizontal tangent. So now let's work on some example problems. Consider the polynomial function y is equal to x plus 2 times x minus 1 squared times x minus 4. So we're given a polynomial function not in standard form, but in factored form. How can we graph this particular function? Well, the first thing we need to do is we need to identify the zeros. That is the x-intercepts. So we're going to set y equal to 0, and we're going to solve for x. So in this equation, what are the possible solutions? According to the zero product property, in order to solve it, we need to set each factor equal to 0. If one of these factors is 0, the entire expression on the right side will equal 0, because 0 times anything is 0. So we're going to set x plus 2 equal to 0. We're going to set x minus 1 equal to 0, and x minus 4. For the first equation, if we subtract 2 from both sides, we'll get that x is equal to negative 2. For the second one, if we add 1 to both sides, we'll find that x is equal to positive 1. And here we just need to add 4 to both sides, and then we'll get x is equal to 4. So that's how we could find the zeros, or the x-intercepts, of the polynomial function. So all we need to do to quickly find the zeros is simply replace the sign. If you see x plus 2, the 0 is going to be negative 2. If you see x minus 1, the intercept is going to be positive 1. Here, x minus 4, just change negative 4 to positive 4, and that will give you the x-intercepts. Now the next thing we need is the multiplicity of each 0. The multiplicity is going to be equal to the exponent of each factor. So for this 0, the multiplicity is going to be what we see here, positive 1. For the factor x minus 1, or for the 0 x equals 1, the multiplicity is going to be 2. And for the last one, it's 1. And so now we have everything that we need in order to graph this polynomial function. So let's go 4 units to the left and 4 units to the right. So the first x-intercept on the left is at negative 2. The second one is at positive 1. And the last one is at 4. Now there's one more thing that we need. We need to determine the overall degree of the polynomial. To find the overall degree, simply add the exponents. 1 plus 2 plus 1 is 4. So we have a degree 4 polynomial. If you were to FOIL this entire expression, the first term will be x to the 4th. And it's positive. all of the signs here in front of x are positive. So we have a polynomial with an even degree and a positive leading coefficient. What is the end behavior for this polynomial? If it's even, it's either up, up, or down, down. Because this is positive, the end behavior will be up, up. So let's put an up arrow above the first x-intercept and another up arrow above the last one. So now we're going to sketch the graph from one arrow, and we're going to try to connect it to the other arrow. So let's approach the first x-intercept. Now what is the behavior of the curve at this x-intercept? In order to find the behavior around that x-intercept, we need to look at the multiplicity. The multiplicity is 1. So the behavior is going to be similar to y equals x to the first power. All we're going to do is draw a straight line through that x-intercept. It's going to be linear at that point. So because the multiplicity is 1, we're simply going to cross the x-axis. Now we need to turn towards the next x-intercept, which is that positive one. For this one, the multiplicity is 2. So think of the graph y equals x squared. The behavior of the curve at the x-intercept is going to look like this. So therefore, we're going to bounce off the x-intercept. So we're going to draw something that looks like a y equals x squared graph there, but upside down. And now for the last x-intercept, the multiplicity is 1. So we're going to cross the x-axis with a straight line. And so that's it. That's how we can graph this particular polynomial function. Now the only thing we don't know is how low the peak is or how high it is. And the only way to get a good idea of the heights of those peaks is to plug in numbers. So we're going to try -1 and +2. And let's see what the y values are for those numbers. So let's plug in -1 into the original expression. So we're going to have -1 plus 2, and then -1 minus 1 squared, and then -1 minus 4. -1 plus 2 is 1. -1 minus 1 is -2. And -1 minus 4 is -5. -2 squared is +4. 4 times -5 is -20. So that's the y value for that point. Now let's see what it is for 2. So this is going to be 2 plus 2 to the first power, 2 minus 1 to the second power, and then 2 minus 4. 2 plus 2 is 4, 2 minus 1 is 1, 2, I feel like I'm missing something here. 2 minus -4 is -2. So for this one, we get -8, which is not as low as -20. Let's try this one. Let's try 1. Actually, you know what? I put the wrong number. I take that back. I see the mistake I made. This is 3, and this intercept should be 4. So this should be 3 plus 2, and then 3 minus 1 squared, and then 3 minus 4. 3 plus 2 is 5, 3 minus 1 is 2, 3 minus 4 is -1. 2 squared times 4 times -1, that's -20. Okay, so these two peaks are of the same height for this particular example. And you could see why. There's symmetry, so to speak. These two zeros have the same multiplicity, and the distance between these two x-intercepts, they're the same. So due to the fact that this graph is symmetric about x equals 1, we can see why these two values are the same. Now this is not going to be the case for every other example. It's just for this particular example. So the best way to determine the relative heights of the peaks is simply to plug in numbers. In this case, they just happen to be the same.